Okay, welcome to this advertisement episode for Lasergurkenland. Are we up and running? Looks like stream is starting, looking good. Let's go. We are joining lgl.zillyhoon.com today, which is a vanilla anarchy server, and yeah, let's continue digging stuff. Oh no, I'm out of tools and I don't have a second device today to do duping, do I? That would be really bad if that thing breaks. Yeah, let me quickly check. It would be nice to dupe some XP bottles. What do we have here? Awesome. Let's see. Do I have battery? Okay. Let's see. Wait, do I have a VPN on here? Oh, whatever. No, my internet is so bad I shouldn't put a VPN on top. Okay. So while that is updating with my slow connection, let me quickly finish my intro. What is left to say? Where's my charger? Back here. Awesome. Yeah, so this is a vanilla Minecraft server, an anarchy server, so you're allowed to use hacked clients, you're allowed to grief, you're allowed to kill other players, and there's no moderation, there's no account with creative or operator status. And yeah, if this is an environment that sounds fun to you, come and join. The server will be online for some time. Currently, as you can see, it's pretty empty, and it has been like that for a long time. Oh, do I have my Minecraft password over here? Yes. No. Wait. Okay. Oh, wait. Can I? Oh. Okay. No way. Let me quickly mute. Okay guys, I am in the game. Alright, so do I have a mouse? Yeah, so that's essentially it for the advertisement part, I would say. Oh yeah, let's mention that there are no word resets. The server's already paid in advance for multiple years, so yeah, the server won't go away even if there are no players. There's no queue, and the server is in the latest version, which is, yeah, the no queue and latest version part is something that most anarchy servers cannot offer due to the high player count. Okay, and the most low player count servers cannot offer a long uptime since, well, there are no donations and no interest in the server, which yeah, usually takes servers down, but not in this case. So this is the one niche server that might be perfect for you. Okay, cool. So we have the second. Oh no, I logged in the wrong account and now I'm in like invalid session. Wait, what happens if I... I'm such an idiot. Oh no. So now if I reconnect, if I logged in the same account, that's bad, isn't it? Yeah, let's see. Okay. So we have this mouse here and this here. What a mess. Okay. Okay, I did it. Awesome. Where am I? No way. No. Oh. Wait, let me do full screen. No. The base got raided. Are you kidding me? My dupe stash is... No fucking way. How do I go full screen? 11? No. Okay. Yeah, okay, that's very inconvenient. Oh no. I mean, it had to happen, but the player count was so low that I felt comfortable. Like, there's nobody playing. Who even raided my base? Ah. Okay, whatever. That's bad. Yeah, and smart move from my side to not store the llama in the disconnected account. Oh, fuck's sake. What a awesome live stream start. Good stuff. Yeah. So I don't know what to do now, to be honest. I mean, sure, I can find something. I probably have another one. Oh no, my internet is so bad. Okay, now we're back. So we have Silk Touch. Oh, okay, that's bad. Come on. Okay, we have one pickaxe left. And if we starting to like... Yeah, no. Then there's nothing left to dupe. Okay, that's bad. Well, okay, I have something to dupe in my e-chest, right? So... that's always given. Yeah, okay, so those are full. I have like... Oh, come on. Oh, that's so annoying. Okay, you know what? I will just ignore the fact that everything is so fucked up now. And just continue like in the last episodes as if nothing happened. Do I have some fire? Okay. Yeah, so I mean, it is what it is. I don't have a llama. I don't have. Should I search a llama and dupe? Well, I can also quickly do that. I mean, those are not super hidden. But you know what? Let's go and start the talk for today. We are already 10 minutes in. That's awesome. And today we're going to watch something from the Media CCC channel, as we often do. It's a video from 2017. It currently has 24,000 views, and I didn't even see it yet. Crazy. Some videos are just hidden. Yeah, the title is 34C3. Oh my gosh, it's so hard to say 34C3 for me. I don't know why. ASLR on the line. Yeah, link to the videos in the description. So if you're interested in ASLR, like address space layout randomization, if I'm not mistaken, then check out the original talk. If you're interested in this Minecraft server, check out this Minecraft server. I hope to see you in game. I will kind of stop moderating right now and just watch that video. So yeah, check out the original and let's go.
Okay, everyone, so now please join me in welcoming Eric, who is a PhD student at the FU in Amsterdam, and he will talk about ASLR. Please give him a warm round of applause.
Okay, this is not really
Hello.
good. That's good.
Like the Herald said, I'm Eric, PhD student at the VU in Amsterdam, at the FUSEC group, and I'll be presenting work that we have done in the group today. The work I'm presenting, most of the work has been done by Ben and Kave, and by Stefan, who showed that the attack that I'm presenting is applicable to all 22 CPU micro architectures that he's tested. So credits to them. I try to sneak this slide in all my talks, but this time is especially apt because this talk is about finding them. So this talk is about attacking ASLR, which is short for address space layout randomization. It's an exploit mitigation technique which, as far as deployment concerned, is one of the success stories. Since it's been introduced, it's been widely adopted, and it makes exploitation somewhat more difficult. The way ASLR makes it more difficult is that it changes the location of code and data usually every time the process is run, so that an attacker cannot rely on certain addresses to be the same all the time. So on the modern 64-bit architectures, the address space usually is 48 bits, which means there is about you can address about 256 terabytes of memory. Of course, this memory is not you cannot write everywhere or read everywhere because your computer probably doesn't have that much memory. So in reality, only a very small portion of the memory is allocated to a process, and so it's quite easy to change the location of this memory. So it makes life for the exploit writer a tiny bit more difficult, because it's very useful for to know the location of data. For example, if you want to overwrite a return address on the stack, then it's nice to know where you can jump to. And of course, if you don't know, you might jump into nowhere and then the program crashes. However, not much is needed to thwart this mitigation. You just need to leak location of the memory. So I really like this backronym. So you can try to reuse the bug that you can use to exploit to first leak information and then exploit, or if that's not possible, you'll have to find another bug which allows you to leak this location. Or maybe you don't have to. So this presentation is about an attack which uses a side channel from JavaScript on processes in the hardware itself to discover information about locations of data or code in memory. So the modern CPU architecture is a wondrous abstraction layer. So even if you, as a programmer, write machine code, there's lots of stuff you don't have to worry about, especially stuff to make your programs fast. Memory accesses are very slow on compared to your CPU on modern computers, and that's why there's a cache mechanism built in. Other things are also abstracted away. For example, if your program does a memory access, the data is written to the cache, but where is it written? Your program gives a virtual address gives off a virtual address to the CPU, which then the CPU needs to translate that to a physical address, which is done by a component called the memory management unit. So the memory management unit has a small cache of mappings from pages to from physical memory to from virtual memory to physical memory. But if that's not if an address is not in the cache, it has to do a page table walk. And the page table walk is what we're going to try to attack, and we'll measure the effect that page table walk will have on the L3 cache, the last and biggest cache in the CPU, to find out what's happening in the during the page table walk. So we're talking about doing a timing attack from JavaScript, and to measure whether memory gets accessed. So, which means that we need a pretty good timer to be able to do this. Luckily for us, the browser standards committees have come up with an API to just do that. So you can take a timestamp, do an operation, and then take another timestamp, and then you get a very crisp time measurement. Until someone published a paper which showed basically that you can do a last level cache attack on the on the CPU and discover some things. So the browser makers made the measurement much more granular. So every microsecond or so, you get a little bump, and then for 1 microsecond, nothing changes. But all is not lost for the attacker, because you can now you can turn the coarse-grained timer into a fine-grained timer. What you can do, for example, is wait for this bump to happen, and then quickly do an operation, and then start a counter. And then, depending on how long the operation takes, the counter, the longer the operation takes, the smaller the count is when the jump happens. So in Chrome, they chose to vary the length of the time when this happens. So, but still, you can do multiple measurements, and then you take an average, and then you can still get a good measurement. However, we can do better. So the browser makers decided to make this a bit more difficult, but where the standards when the browser standards committee taketh, they also giveth. So they decided to implement an object called the shared array buffer, which allows multiple threads, which are called web workers in JavaScript, to work on a single piece of memory. And they decided to enable this by default, which is actually after we published the attack. So they basically have given up on preventing nanosecond scale time measurements in JavaScript. So the shared array buffer can be used for other things, but I'll not talk about this today. So how can we measure time using shared memory? Well, it's quite simple. One thread is used for doing the timer measurement, and the other thread does the operation. And then, so when the thread which does the operation, the timer thread waits until the thread which does the operation is ready to do the operation, and then it sets a variable and starts the operation. Meanwhile, the counter thread, the timer thread, sees that the shared buffer has changed and will start counting. And then when the operation is done, the second thread changes the buffer again, and then the counter thread stops. So this gives a very crisp measurement. So now we have a nanosecond scale timer, and we can do side-channel attacks from JavaScript. So we'll be doing a timer attack by on the last level cache, and when the CPU accesses memory, everything is on on the granularity of a cache line, and which is 64 bytes. Within, for example, the level 3 cache, a certain physical address maps onto a certain cache set, and this cache set can, for example, on a 4-core desktop Intel machine, contain 16 different cache lines. And I'll talk about a modern Intel machine, but the concept translates to also to other microarchitectures. So per core there are 2048 cache sets, which are called a slice, and so on a 4-core machine you have 4 slices, and these slices are shared among all the cores, but it's just the way Intel has organized their cache. To get the cache set ID, so which cache set within the slice is used, you take the physical address and then you discard the 6 bits which are basically telling you which byte within the cache line you use, and then take the 11 bits next, and that is the cache set. So it's basically a round-robin mapping of the physical memory. The cache slice is some complicated hash function, and for this attack we don't need it, so we're lucky. The important thing to remember is that the if 2 cache sets, cache lines, if physical memory map to the same cache set, they have the same offset. So the same physical address if you only regard the bits which are so they only regard the lowest bits, so that every one they have the same address modulo 128k kilobytes. So from which follows that they also must have the same address modulo 4 kilobyte, and which happens to be the size of a memory page, which is the base unit of memory management on almost all architectures, I guess, in use. Now we know this, we can do a cache side channel attack, and there are multiple attacks possible, and we'll probably use the most simple one, called evict and time. So the code to do the evict and time attack is also quite simple. You have an evict function which uses a buffer and just accesses cache lines which map into a certain cache set, and we can just do that by accessing the cache line which at a certain offset of a page which we've just seen, and at this point all the cache lines should be filled with our data. So then we proceed to do an operation. We take a timestamp, we do an operation, and we time how long this takes. If this operation needs to do something with a physical memory, a cache set which maps into this, a cache line in physical memory which maps into this cache set, it will take longer because we'll have to do a memory access, and the memory accesses are really slow.
No.
Compared to the CPU or cache hits on modern computers. So this way we can see if this operation depends on the physical memory location which maps into this cache set. So how does this apply to the page table walk, which we'll attack? So page tables are a mechanism a mechanism for processes to address a really large address space while only having a relatively small amount of physical memory. So it's basically a tree structure with tables at every level, which divide up the address space into equal parts. So the first level on Intel, so, which is called the fourth level because there are 4 levels. Well, so divides address space up into chunks of 512 gigabytes. The next level, there could be 512 entries, but there don't have to be. Divide the address space into 1 gigabyte chunks, then into megabyte chunks, and then lastly into 4 kilobyte chunks, which is the granularity of a page. So each entry in there points to a memory page, a physical memory page. So what the page table walk process does is it takes the address and will look at the we'll use a binary representation of this address because that's easier, makes it easier to show the process. Where the 1 bits are black and the white bits are 0. So say there's a TLB miss, so we'll have to do the page table walk. Now there's a special register in the CPU which points to the first page table. Then the page table, the hardware looks at the 9 most significant bits in the address and then uses that as an index pointer into the table. Then it does the same with the next level, and with the next level, and with the next level, up until the level where we know the actual page, and then the 12 bits at the end will be used to point into this page.
Okay.
So this is a 4K page, but and so we can use this page to do a side channel attack. But what but the observation is that the other the page tables themselves are also pages. So yeah, each of them are pages,
so
and so we can also do a side channel attack on these pages.
I hope it works today.
So let's take a look
Maybe
of
duping
what
works
we
better with bad
can
internet.
discover this way. So we can find out that a certain page gets a hit. Now there are 8 possible entries which would cause this hit. So we don't know that much, but so of all, but if we look at these pages, we can see that 6 bits are the same. So we now know that there is a sequence of 6 bits in this address that has this value.
Why is it so dark?
That we discovered by doing the cache timing side channel. Now there are 4 levels of pages, and there's a final location into the page. So we get 5 cache colors. We assume we know the last level, the last location inside the page, because that's in practice pretty easy to reverse engineer. And even if you can't, there are other side channels to find this out. In fact, we use this final location to do the side channel attack on all the other locations.
Yeah, it's okay. No, I guess.
So, or actually, we try to, try to not get in the way.
Okay, it makes barely a difference.
So
all right.
Now we have found 4 cache lines, which may be used for the page table walk. So we can see that there are 4 chunks of 3 bits that we know nothing about. And what we also don't know is which cache line is used for which level of page table. So that would give us about 16.6 bits of entropy left. So
Okay.
that's not a whole lot that we have gained. We still need to find 16 bits. However, there's kind of a trick. So we have a technique called sliding, where we allocate a large enough buffer, and then we just probe pages one after another time. So we just try the next page, try the next page, try the next page. It looks a bit like this. So for the last level cache page table, we just try the next page, the next page, the next page, and then when it switches, we know, okay, this was a cache line boundary. So for the next page, we know that the lowest bits of this entry are all 0 because it's just went over the boundary. This technique we can also do for the second level page tables.
Oh, come on.
This time we add 2 megabytes, 2 megabytes, 2 megabytes, 2 megabytes. Still not that problematic to do from JavaScript. And then we get the whole second level page table entry. So how much entropy is left? So, well, we have got 2 chunks of 3 bits, and we don't know which page table, which cache line belongs to which page table
Yes, it worked.
level.
Nice.
So we are left with 7 bits, and this is. So I think for this, there's not a lot to do about this if we want to have good timers in JavaScript. But we can actually do more because in practice, stuff doesn't. In practice stuff isn't optimal. So so actually nowadays we're starting to be able to allocate 1 gigabyte allocations in JavaScript, which is probably because you want to run a real tournament in there or something. But then for the last level, it's kind of too much. 512 gigabytes allocations, and then you might have to do that up to 8 times. So maybe not. However, actually, for example, for Firefox on Linux, if you allocate a certain type of object called an array buffer, Firefox doesn't initialize the memory, and it just asks the kernel for the memory and then just leaves it there. And what the Linux kernel does is it doesn't initialize it, and so it doesn't have to map in pages in the page table structure. So it just and it doesn't use up any memory as long as you don't touch it. And we don't have to touch it. We just have to go over and touch one page or one page at the very end. So this seems to So actually on Linux it turns out you can allocate huge chunks of virtual memory, and actually within seconds to minutes you can calculate the whole. You can basically do the sliding attack and flip the cache line on the highest level page table. In Chrome, Chrome does initialize memory, which is a bit unfortunate for us, but what it does is it divides memory up in heaps, and when the heap is full, or it decides, okay, maybe for security reasons I'll need to create a new one, it just to increase ASLR, actually it tries to allocate a huge, it tries to leave a huge gap between the previous heap and the new heap, which means we can move forward quickly in the address space. So using this method of creating new heaps, or we can recover the third level address bits, which would leave us with 3 bits of entropy left. And on Windows 1 or 0, I am not sure. But doing the attack on the 4th level would take a lot of time, and maybe the person because Chrome needs to initialize and free lots of memory, and it just takes time, and your laptop gets hot, so maybe the user will click away, and no ASLR for you, recovery for you. So this attack was implemented on a Skylake machine, but has been verified that it works on 22 machines by testing the side channel on a native C with a native C program. So yeah, so time for a demo video. So
okay, let me stop duping now, because I was told the demo video is interesting, and also the duping is the worst.
So here we have obviously the browser. So these these bits are the raw measurements, and what you see here are signals detected by a solver, which kind of tries to find the most likely values for the attack. So looks really pretty matrix style.
Okay, I don't get the demo.
And then the solvers try to get confidence on what they're measuring up to a certain point, and then they decide, okay, it's clear. And then attaching GDB to the address, we can see that the address is a location of memory that we know. And because of that, we left a marker there. So that's so yeah. So in conclusion, it's possible to recover quite a lot of address information from JavaScript using a hardware side channel alone on the memory management unit, and apparently browser vendors have given up on this and on other side channel attacks, because you can't have you can't have multi-processing with shared memory without this, and apparently that's the way, the direction we're going. So yeah, any questions?
Yes.
As always, please line up at the microphones. We'll start with number 1, please.
Yes, have you looked at actual browser bugs and looked at how many are exploitable with just a single leaked pointer? I mean, usually you need at least 2. You need a code pointer and somewhere to write to actually gain control over the execution flow.
So in our attack, we also have a way to leak a code pointer. So we first leak a data pointer, and then we create lots of JavaScript pages, JIT JavaScript code, and then we yeah, so leaking the these most significant pages is really hard to do for code, but the last level, so the ones yeah, the page tables which are yeah, which point to the actual pages, and I think also the levels, the level one level above is actually pretty easy to, well, easy. It's doable to leak using this technique.
Could we get mic number 4, please?
So you just criticized the browser creators for the well, not trying to mitigate all these security issues. What would you, as an ASLR hacker, recommend the browsers to do? What are the measures they could take that they have not yet taken?
So, yeah, there's also a discussion of whether ASLR, so one of the things that make this attack quite easy is that browser makers have tried to prevent against another problem called use after free vulnerabilities by allocating more memory in a different region every time, because if you can free memory and then allocate, if you allocate something else, and then a bug in the browser will use it as if it were the old object, for example, then you usually can do quite bad stuff. So I guess so you can think of mitigations against this technique, but they might work against the mitigations against use after free. So the question also becomes, do we, so is it still worth it? So yeah. Also because there are only 7 bits that are not inherent to the architecture. So yeah, the question is, in an environment where you can run JavaScript, is ASLR, yeah, it might help a bit. And sure, Ben and Kaveh spent lots of hours on implementing this, so an exploit writer might, yeah, it will still be extra effort if there's no easier way, but yeah, the question, yeah, I'm not sure.
Could we get a question from the internet, please?
Given that ASLR is only meant to help protect against remote attacks, how useful is your approach when an attacker cannot exercise the MMU?
So the attacker would always exercise the MMU, but I guess choosing the location is harder, and and the timing is, of course, over the network way more difficult. So I don't really, yeah. So, but the thing is that ASLR is used for local attacks, and this against local attackers, and this shows that it's that are inherently inside the architecture problems with this, and that it's not that useful apparently.
Can we get mic number 1, please?
So recently I saw a vulnerability by the security researcher Loki Hart, which was for iOS. And in your presentation I saw, of course, the Apple Cortex, the Samsung Cortex A7, which is the iPhone 5's processor. What I'm wondering is, if I create an array in JavaScript containing my shellcode, am I able to, with this attack, to get the address of that specific array, or is that impossible?
So So usually, I guess shellcode itself won't be executable in an array, but so you will get location of memory that you control completely, if that's what you.
Okay. That's actually what I meant.
Okay.
Yeah. Cool.
Okay.
Is there a POC available, or is this kept closed source?
And I don't think we usually don't release the attack code. We do describe. We described it in the paper, so it's it should be reproducible using the paper.
Right. Thank you.
Okay.
And we'll just stay at mic 1.
I didn't get the graphic you showed us in JavaScript. What were the colors and what were you trying to say there
The
in the Y and X axis?
That's
Good question. Thanks.
Can you say stop or?
In your video, for example, or
The demo.
Oh yeah, so so I'm not completely sure about the first one. Might be raw measurements.
What?
The second
He doesn't
one
even know?
are the
Are you kidding me?
the four, I think. Well, are the page tables that that we try to the lookups that we try to find. Yeah. So you, yeah. Okay.
And more from mic 1, please.
Hello. I was just wondering if you guys actually tested this technique on public clouds or any multi-tenant architecture.
So this attack is within the browser. So yeah, we tested it as if it were a client, a browser client. Okay.
I mean, like I would like to continue actually, if it's okay.
We have a lot of time.
All right. So I read a couple of things about this. My question was not really specifically about the ASLR, but more like how could be like the mitigation techniques for like public cloud where each tenant has the right access to the cache line, and how is that? Do you think possible to disclose the cache line?
So yeah, there have been quite a few attacks using. Using this technique from also just natively, like you would do in a VPN environment, for example.
Is the guy
VPS environment. Oh, sorry.
You're on.
So there is a browser plugin from some researchers at TU Graz called JavaScript Zero, which aims to provide mitigation against sidechain attacks from JavaScript. Have you heard of it? And if so, have you tried if it provides protection against the attacks you showed?
So I think, yeah. So I haven't tried it, but what I described, I would say it would. Provide protection because it allows you to disable stuff you don't want, among which the shared array buffer. So in principle, the shared array buffer wasn't here before this year anyhow, and so I doubt lots of public code makes use of it. So I think it's easy to disable stuff you don't want. So JavaScript, they're basically adding stuff all the time. So to make it suitable for gaming and all kinds of sensors that you want, and and most code doesn't make use of it. For example, I only use JavaScript in my browser when the page doesn't load without. But yeah.
Yeah, so all the time.
I'm all for disabling lots of stuff that we don't need, but the direction of the browser seems to go the other direction. So I guess we'll see how it will turn out in the end. So. Okay.
Do we have any more questions? No? Then please thank our speaker again.
Alrighty, wonderful. That's it for this advertisement episode as well. Make sure to check out the original talk. And make sure to check out Lasergurkenland. I hope to see you in game.